Example, what is the delta G for 2CH3OH plus 3O2, in other words, the combustion of methanol gas. This is gas, 2CO2 gas plus 4H2O. So we want to know what the standard, free energy change is for this. Okay, now the entries, I'm going to actually write out the entries that you would see in a thermodynamic table, just so you actually see it. I mean, I know that you can flip to the back of your book, but I'd like you to see the numbers anyway. So the entry for, well, actually I'm going to do the entry for all of them. So let's go CH3OH as a gas, O2 as a gas, CO2 as a gas, and oops, here we go with the straight lines again. We don't want that. CO2 gas and H2O gas. Now we have entries that look like this. There's going to be something that says delta H formation, and it's going to say kilojoules per mole. And then there's going to be an entry that says delta G of formation, and that's in kilojoules per mole. And then you're going to have S, which is going to be in joules per mole Kelvin. You know what? I really need to make this a little bit more legible. I understand. My apologies. S, and notice there's no delta S. It's just S. This is going to be in joules per mole Kelvin. So we have minus 201, 0. Remember, 0 elements. The enthalpy is 0. And we have minus 394, minus 242. The delta G is minus 163, and the delta G for elements is also 0. This happens to also be 394, which is really interesting in and of itself. Minus 229, and then we have 240, 205, 214, and 189. The entropy of an element is not 0. Oxygen gas is a disordered system. There are a lot of particles of gas. 205, that's a lot of entropy. So it's not 0. It's not the same as these. When I run this, when I take 4 times the delta G of H2O, so I'm working in this column right here. I just wanted you to see what the other entries are. 4 times the delta G of H2O plus 2 times the delta G of CO2 minus 2 times the delta G of CH3OH gas minus 3 times the delta G of O2. When I actually run the reaction, I end up with, or run the calculation, I end up with a delta G. Notice the F is gone. Those were delta G's of formation of the individual elements. That's what's in the table. The final outcome is just my delta G, my free energy. And it's not in moles. It's not in kilojoules per mole. It's just in kilojoules. And the reason is because I've accounted for the moles from the balanced reaction. I'm taking 2 times something, 3 times something. I'm using the stoichiometric coefficients. I end up with negative 1,378 kilojoules. 137,800 joules. That's a lot of energy. That reaction, the burning of methanol, is highly spontaneous under standard conditions. So that's what this means. Let's see. Okay. So now we have a good sense of dealing with free energy. We treat it the same way we treat delta H or H or S. We just take products minus reactants. We also have the equation delta H minus T delta S to calculate it that way. Now let's think about what this actually means. This number here tells me that it's spontaneous as written. That means it'll happen eventually if I don't do anything. Now that doesn't mean it's going to happen quickly. It just means that it will happen and I don't have to do anything about it. Thermodynamically, it's spontaneous. So spontaneity is a thermodynamic statement, not a kinetic statement. It just says that the energy of the, from your perspective, the energy of the CO2 and the water is lower than the energy of the methanol and the oxygen gas. So it's a downhill thing. We just needed to get it over that hump. That's the kinetics part. Okay, so now let's think about what this means. This delta G is a measure of the tendency, the potential for a reaction to move forward. Well, let's say it starts moving forward. Well, as it starts to move forward, more, CO2 and water are going to form. Methanol is going to be used up. Oxygen is going to be used up. Let's say that half the reaction has gone forward. Does that mean at that point that the free energy is the same? As it turns out, no. The idea is free energy wants to get down to zero, or in this case, wants to get up to zero. A zero free energy means the system is at equilibrium. So you can have a negative free energy. That means that the reaction as written wants to go to the right. It's spontaneous to the right. If it's positive, that means the reaction wants to go to the left. The idea is the reaction wants to get to a point where the delta G is zero. So as a reaction proceeds forward, the delta G actually changes until it gets to a point where it's zero. That's equilibrium. That's what all reactions do. They move toward equilibrium. So, let me write this down. As a reaction proceeds, toward equilibrium, the delta G changes. The delta G changes until it hits equilibrium, until it reaches zero, which is the equilibrium point. Okay, now, we have been calculating delta G with that little zero on top, standard delta G's under standard conditions. 1 atmosphere pressure, 25 degrees Celsius, 1 molar concentration for aqueous species, standard conditions. Well, what happens when we run a reaction not under standard conditions? What if it's at 200 degrees Celsius? What if it's 3 atmospheres of one gas and 17 atmospheres of another gas? What happens then? How does it affect the delta G? Is it affected at all? As a matter of fact, it is. So when we change the conditions, when we change the pressures, the temperatures, the delta G of the reaction as written changes. And rather than going through a sort of discussion of, a derivation of this equation that I'm going to write down, I'm just going to write down the equation because we just want you to be able to use it and understand that the delta G, this delta G is under standard conditions, but we're not always running reactions under standard conditions. We often, most of the time we're not doing it under standard conditions.